Hi everybody. Today we're going to take a look at an introduction to rotational kinematics. And I think that by the end of this lesson you'll be pleasantly surprised when you realize that a lot of the quantities that you're very familiar with all have an analog when it comes to rotational kinematics that we can use. And a lot of these equations that you're super familiar with can also kind of be reimagined thinking about rotational motion. So if we imagine that we have like a ball rolling across the classroom floor, like maybe one of our infamous bowling balls in our class, we can imagine this ball's motion against this horizontal floor. And it might be pretty interesting to collect some data about the number of rolls and then the delta x or the linear displacement and the total angle. So, for example, we can think about if the ball rolls one time around, so one complete rotation here, then the delta x would be equal to this circumference of the ball. So I know that circumference is equal to pi d, or 2 pi r. So if I have one roll, the delta x is equal to 2 pi r. Okay, and now the total angle here would be 360 degrees. So if I think about from here, one full rotation all the way around here is 360 degrees. Okay, I think that we can imagine if the ball undergoes two rotations, then the delta x is equal to 2 circumferences. So basically 2 times 2 pi r. So that's going to give us, for 2 rolls, we're getting 4 pi r. So instead of 360 degrees, we've got 720 degrees of motion there. Okay, well, we could start to get creative here with some numbers. Let's imagine that this ball undergoes a rotation 1/2. So if delta x is equal to 1/2 of the circumference, so if the number of rolls here is 1/2, instead of 2 pi r, this is going to have a linear displacement of pi r. And that's going to be an equivalent of 180 degrees, so half of that full 360. 1/6 the number of rolls, it's a little bit tougher. Basically, it's going to be 1/6 of the circumference, so 2 pi r over 6. So if I have 2 pi r over 6, this kind of reduces down for me to pi over 3 times r. Right? So you could say pi r over 3. And instead of 360 degrees, it's 1/6 of that. So I've got 60 degrees of rotation here. So if this were an observational experiment that we conduct in class, at this point, might be looking for a pattern. And the pattern may not be that visible to you right now. I mean, some of you might see it right at this point. But it may become more apparent here if we think about radians. So if we can think about, okay, if I have this object and it undergoes a rotation of 360 degrees, then in radians, I'm talking about 2 pi r radians. For that complete circle, I've got 2 pi r radians. So 720 degrees would be double that, so that's 4 pi radians. I don't know why I put r here. I'm talking about radians here. But yeah, so 2 pi radians for the first one, 4 pi. If I'm undergoing half a rotation here, then this has a value of pi radians. And then finally, the 60 degrees is our pi over 3 radians. So now I'd ask you, what pattern do you notice here? Well, once you calculate the rotation in radians, it becomes pretty apparent, pretty easy to see that when we take a look at our delta x value and compare it to this column over here, we notice something pretty impressive about the relationship between the linear displacement and the angle that the object moved through. So you can notice in each of those columns they're the same. When we have this rolling object, the linear displacement depends on the angle that the object moved through. So when we only have a rotation of 2 pi, the delta x is 2 pi r. And rotations double that produce 4 pi in terms of the angle and 4 pi r in terms of the displacement. So we can express this pattern in terms of a math model here. So when we look at all the data we've collected, we find that our delta x is equal to the radius times theta. But it's important to note, let's talk about exactly what these are. This delta x is our linear displacement. R is the radius. And this theta here, this is the Greek symbol theta, this is the angular displacement, is what it's called. And for our angular displacement, this is in radians. Okay, so each of our linear quantities that we're familiar with, displacement, velocity, and acceleration, all have an analog when it comes to angular quantities. So we already know that displacement for us is a change in position. So it's just change in position, and we can model this as, we say delta x is equal to x final minus x initial. We're talking about the linear quantity. Well, what we just found in the previous experiment is an angular displacement. So instead of delta x as the symbol, this has the Greek symbol theta. And instead of being a change in position, this is a measure of the change in angle. And we know that we have this formula for angular displacement that we found, this x equals r theta. So this is one of our new formulas here. Okay, now if I go down to velocity, velocity is a change in position, so obviously the displacement divided by the time. And our math model for this velocity here would be the v equals delta x over delta t. So our change in position with respect to time. So we have a matching quantity for this in terms of angular velocity. See, we're not too creative with the names here. And instead of v that you'd use for linear velocity, the angular velocity is kind of this weird symbol. It's a little omega, so it kind of looks like this little w, but it's a bit curvy. So when we talk about omega here, it's going to be a change in angle with respect to time. So very, very similar, just how velocity is displacement over time. Angular velocity is angular displacement over time. So this would just be the change in angle with respect to time. So if v equals delta x over delta t, then this little omega, this angular velocity, is the change in the angular displacement over time. Okay, so you can probably guess what's coming next. We're going to talk about acceleration, and we know that the operational definition of acceleration is a change in velocity with respect to time. And we use a math model for that, A equals delta V over delta T. So you can probably already guess where we're going with this. We have a quantity called angular acceleration. And yes, of course, this one too has kind of this funny symbol with it. It's an alpha symbol, so we draw that like that, so that alpha symbol is your acceleration. And this is a change in angular velocity with respect to time. So you can probably already guess what the math model for this is. Yep, you guessed it. It's going to be angular acceleration, this alpha here, is equal to change in this omega angular velocity over time. So each of these quantities on the left has this matching quantity when we think about rotational motion. So there's a couple of other things I want to talk about here. If we have a math model for angular displacement that we derived from the last experiment, x equals radius times theta, then we should be able to come up with a formula for the velocity. So velocity is equal to the radius times the angular velocity. And so we can get acceleration is equal to radius times the angular acceleration. So here's that alpha symbol again. Okay, so we found from all of our linear quantities an angular quantity kind of match this. So we have our linear displacement, angular displacement. We have velocity and angular velocity, acceleration and angular acceleration. So I just want to take a quick minute to talk about units here. We know in terms of units that for this angle that we found, the units are going to be in radians. So you may see this radians here as RAD. For the angular velocity, if the angular velocity is equal to change in theta divided by change in time, then the angle that you'd get here is going to be probably what you think it is, radians per second. And then the units for the angular acceleration, well, if angular acceleration is equal to the change in the angular velocity over time, then this is going to be radians per second all over seconds, or radians per second squared. So I'm sure that you remember these three kinematics formulas that we use a lot. So you have your VF equation, your VF squared equation, and then finally the delta x equation. Can we rewrite these using the angular quantities? Yeah, we definitely can. So we would have angular velocity here equal to the angular velocity initial, plus instead of AT, we'll have our angular acceleration times time. Instead of VF here, I'm going to have our angular velocity here squared equals our angular velocity squared initial plus 2 times alpha and then theta. And lastly over here you've got delta theta, so your displacement perfect.